Hello everyone and welcome to this video. If you have ever run a finite element analysis and wondered, can I actually trust these stress results? Then this video is exactly for you. Today we are going to analyze a complete G-clamp assembly in ANSYS Mechanical, and instead of simply making the mesh finer everywhere, which is what many beginners do, we will learn how to refine the mesh intelligently. So we will compare multiple mesh refinement techniques and determine which approach provides the best balance between accuracy and computational cost. So in this video, we are gonna do the comparison between the following techniques, which they are the initial coarse mesh, global mesh refinement, local mesh refinement while using only face sizing, body sizing, and sphere of influence, and finally doing the refinement control method. We will compare the highest stress in each one of them, the solution time, memory usage, number of elements, and nodes. So later in this video, one refinement method will give nearly the same accuracy with less number of elements. So before we touching like any mesh settings, let's first understand our model. So we are working with a G-clamp assembly, and under load, the G-form that we have should try to open, and as a result, we already expect some obvious stress concentration locations. So without even running the simulation, we can already predict where high stresses are likely to occur. Typically, this is like will include these two small radius here. So these are exactly the regions where our mesh resolutions matters the most. On the other hand, like large flat region like here usually experiences smooth stress gradients, so meaning they don't require a very fine mesh. So understanding this simple principle can reduce your computational time dramatically. So now before we start with the study, I already put on the description down a link so you can find the CAD file in case like you are interested like to do the study by yourself or with other like parameters. So let's start now with this study, and we will begin with the initial coarse mesh. So all what I have or I want to do actually is to go to mesh, and I'm gonna to change one parameter and keep it like as a constant like through all the techniques, which is like the element order. I'm gonna to change it from program control to quadratic just to make sure that's like stable or stay the same overall like techniques that we will like test. And I'm gonna choose like seemingly like a coarse like element size, which is in my case here it should be around 5 millimeter, and I'm gonna to keep everything else like as it is by default. So we go to mesh again, right click and generate mesh, and now we got this like it's already like a coarse mesh, it's obvious, so this is fine. And now we are ready actually to solve the model. So what we have like actually to see, we can like put a total deformation and equivalent stress. This is would be enough, and we can collect the other information later on from the solution information. So let's solve this first, and I'm gonna in between like we wanna like to collect all this information. So I already prepared these tables so we can put it together and see the difference with each techniques, like what happens for these parameters. So now we got the solution. I will go directly to the equivalent stress. Okay, it's interested, like as you can see, we already have like the high stress on this like location, and it's actually about 49 like megapascal. So let's put this on our table, 49 megapascal. And to collect the other informations, I recommend to go to solution information, and from there, if if you will have like something called solver output, so you have like to go to solution history so you can see them. After clicking on it, like you will get the following informations, and this is what we are need like now for our study. So I'm gonna first put the number of elements, which is 2832, and nodes 5488. Solution time was here like 18 seconds, and memory usage about 0.19 gigabyte. Okay, perfect. So the first techniques is done. Now let's go to the second techniques, which is the global mesh refinement. So I'm gonna go back to mesh, global mesh refinement, and what we mean actually here actually is to globally like change or reduce the element size. So on all parts. So let's clear first this mesh, and I'm gonna to reduce the element size from 5 to 2 millimeter and generate the mesh again. Let's see together, and as you can see the mesh it's like way fine like as before, and we are ready now to solve the model. And we should now like insert here the new results. So what I need from the solution here is actually seeing the equivalent stress, like how much is it. So it's done. And the equivalent stress, as you can see, is still on the same like locations as we expected before, and the value is actually 63.14. So I'm gonna to hit here and type 63.1 megapascal and get the other information. From solution information you will find under the solution number 2 there the new like information. Gonna to put the number of elements and number of nodes, solution time 20 seconds, a little bit more than before. It's like actually logical, and we used actually more RAM. So this is perfect. Now we are done, and we are ready now to jump to the next techniques, which is using a local mesh refinement, but the face sizing like specifically. So we go again to mesh. I'm gonna now to clear generated data, and because we are like changing the locally the mesh or make it fine like locally, so I'm gonna to keep it back here like by 5 millimeter as the first like techniques, which was the coarse mesh refinement. And I'm gonna to go to mesh and insert a sizing and choose surface, these two surfaces where I expect like high stresses, and I'm gonna to put the same element size 2 millimeter and generate the mesh again. So as you can see globally like it's still like coarse mesh, but like only on these two like small radius here we have like this fine mesh with a size element of 2 millimeter. Now let's solve this model. So now we have to input the result here. And let's see how much stresses we will get. Okay, perfect. So we got actually like a little bit more like stresses here. We have like around 64.57. So let's go and put 64.6 megapascal and go back to solution information and put the number of elements, the number of nodes, solution time, which is 18 seconds, and memory is 0.2 gigabyte. So perfect. Now, the next technique we are going to use actually using body sizing instead of the face sizing. So I'm gonna back to mesh. I'm gonna delete the face sizing. And in this model, we are having like just two parts. This is will be like visible on other like assemblies where you have like multiple parts, but let's clear first of all this mesh. And however, I'm gonna to choose body and choose only this body and insert a sizing and change it here to 2 millimeter overall and generate the mesh again. So, and now in this situation, oh, as you can see, this part is like so dense. The mesh is too fine, like everywhere, not only on this radius, but everywhere. And this is like still coarse. So let's try now to solve this model. And as you can see, it's like until now, the bigger model, like when we are like speaking about the number of elements on nodes, it's like huge. So let's see what we got or get from this this technique. So now we got the result. We have here the stresses, which is like 60.927. So I'm gonna to put this on the table, 63.9, and the rest information there. We have a number of elements of 74,449, which is like huge for this like just simple part. 784, and solution time was like 32 seconds and 0.65 gigabyte of RAM were used. Okay, perfect. Now let's go to the next like refinement techniques, which is like using a sphere of influence. So let's do this together. I'm gonna go back to mesh and I'm gonna to delete the body sizing and clear the mesh. So in order to create like a sphere like of influence in the mesh sizing, we need actually to define first like a coordinate system. So in my case, and because I have like two different like or separate like a location where I wanna like to use this spherical of influence method, so I'm gonna to create two coordinate system. Let's go first to this like the right side. I'm gonna to choose the edge and choose these two edges, just like to make sure like I got like nearest possible a coordinate system there. I go to coordinate system and insert a coordinate system. So we got the first one, and I will do the same on the other side. Go to coordinate system, and we have the second coordinate system here. Now, after defining the coordinate systems, let's go back to mesh and insert there. I'm like on the geometry, I have to choose the whole body. And now I have to change the type from element size to sphere of influence. And after that, we must like choose the coordinate system. And for sphere radius, I'm gonna to choose 6 millimeter here. And as you can see, this is like how big the sphere of influence on our model. You can like make it like smaller, bigger, it depends. Let's stay here with 6 millimeter, and element size, let's give 2 millimeter. I will do the same on the other side, so I'm gonna just to duplicate this, and all what I have to do actually to change the coordinate system from this to this, and yes, now it's ready. Now we are ready actually to generate the mesh with these like settings. So now we are gonna back like to coarse mesh, like overall just on these regions, like where we like already defined that the spherical like influence, we have this 2 mm like as element size already defined. So perfect. Let's solve now the model and see what we get as stresses. So now I'm gonna go to equivalent stress. Now we should like put the information here. Okay. So we have solution. Let's go and see it. So I have 63.167, so around 63.2. So 63.2. And from the solution information, let's gather the other like informations, which they are like elements. Like I have 6,676, number of nodes 10,801, solution time 20 seconds, and amount of RAM used are like 0.21 gigabytes. So save. So this is like done. Now like the final one, which is like using the refinement control method, which are the final techniques in this video. So let's do it together. I'm gonna go back to mesh and you clear everything. And I'm gonna to delete these two spherical form. And now the refinement like methods, you will find it actually when you click on the mesh on the top toolbar, you can see we have this refinement, and also you can find it when you click on the mesh, insert, and refinement there. So you have like two places so you can find it. Now on my global I still have 5 mm. I will let it like this, and I'm gonna actually to choose surface refinement. So we have refinement there, and I'm gonna to choose these two, only these two surfaces, and I'm gonna increase a little bit the level of refinement there from 1 to 2 as an example, and let's now generate the mesh. So you don't give here like an element size, you just give like a refinement like level. And as you can see, we have like a coarse like body, but we have like actually fine mesh not only on these two surfaces, but also actually a little bit inside the solid part, which is good when you have like high stress as a gradient actually. So let's see now what we get like as a result from this technique. It's actually interesting, especially in cases where your stresses are like not on the middle, for example, where it's like locally at specific location. So refinement like will do like this. Very good. Okay, perfect. So we have results. So from these techniques, we got like about 64.4 megapascal. 64.4 megapascal, and from solution time we get like number of elements 10,602 and nodes 70264, and now from this location actually we got solution time 20 seconds. Of course time it depends like also how much cores you already have, so it's like hardware thing, but this is for our study. It's like the same overall. Memory usage now it's like 0.24 gigabyte. So perfect. Now we have all datas like actually for all these like 5 refinement methods that we already like talked about on the beginning of our like study. But in order like just like to make sure like comparing to what like stress, for example, we should like compare if it's like correct or not, we can like make first, like before we do the comparison, like a mesh convergence study. And this convergence mesh study, we can do it like this. So I'm gonna actually go back to my mesh. I'm gonna to remove this refinement, and actually I will generate it, clear generated data, and generate again the coarse mesh. And what you can do is the following actually. So before we solve the model, you can go to the equivalent stress, and you can insert from there something called convergence. And by default, actually, the allowable change is 20%, which is actually so high. So when you have like a 19 or 18% change, he will get it as a, like already converged, but it's like 20% is a huge. So let's like make it like a smaller value here. Like instead of 20%, let's tell him that we accept results like that can like vary maximum 5%. So I'm gonna to put now 5%, and now we can click on the solution and hit solve. And now while he oh sorry, like we forgot like actually to collect something. Like before like we solve the model, you have to specify the number of loops, because by default and the solution, the maximum you will find under solution, you will find the maximum refinement loops. By default, it's 1. So even it's like not didn't like achieve this 5% because it's already 1, he will do just 1 loop. So 1 like iteration. So let's increase this to 5 just to make sure in case he didn't like get it from the second time, that he will go to the third, fourth, 5. So let's see what we get from this. So I will stay like with the refined depth 2, but I will increase this max refinement loops to 5 and solve this model. Now you can see actually what happens like while he like calculate like on each iteration what he get as a stresses. So all what you have to do is to click on the convergence, and from the convergence here history, you will see on a curve what it happens actually every time he calculate the stresses. So on the first iteration, he got like, as we did like on the first techniques with the coarse mesh, around like 49 megapascal with these numbers of nodes and elements. Let's see on the second one. Like he's now this is the first iteration. Now this is the second iteration, and as you can see, the change is at 22%, which is like above the specified value from us, which is like was like 5%. So he must like calculate like again, but we are using like now more nodes and elements. So let's see now for the third iteration. Okay, this is almost 5%, but it's still like a little bit like bigger than 5%. So you must like calculate this like also again. As you can see now, the stresses were before like at the beginning were about 49 megapascal, and the second 61. Okay, so I'm having now a license like parameter. So however, like it's almost 5%, so we will get these results as our like final results. So I'm gonna to put the following. So these are our results, but the result that we should expect, actually, let me say that we expect to have like 64.3 megapascal. And these are actually okay. We don't need to know now the number of elements and nodes, but it's okay to know like what the correct or almost correct like stress to get at this small radius. So now we are ready actually to compare all this method and summarize like everything we have learned. So as you can see now, Let's do the comparison together and see. So the right stress, or the best stress result, should be like around 64.3. With comparing all these results, we can see that using only the initial coarse mesh, we got like just 49, which is like a way from our our like specified or our should result. So I will like take this out because the stresses are like too much like far away, which is like wrong. So I will mark this as like in orange. Now looking into all the rest like calculation, these like actually refinement method, these like methods at these locations, we can see that we have almost the same like stresses, like just like a small difference between each of one of them. So we have to compare other parameter. So for example, the solution time and memory usage. As you can see here, like we have that these three like calculation have the same time, or the solution time were like 20 seconds. The faster actually was like the local mesh refinement while using phase sizing, which was like 18 seconds. And the slowest was when we like define the whole body with 2mm element size. So this is the worst one. I will get this like, even if I have a good like stress value or near to the accurate value, but it was like so slow, and we already used a high number of element and nodes, as you can see. So we will take this like out, and now looking into these values, as you can see now, we these two actually they were like by 63 megapascal, while the other one, this one and this one, were by 64, so near to the exact value. So actually we can like take also these two values like out, like this and this, and now that challenge is actually between the local mesh refinement using phase sizing and the refinement control method. The values are like too like near to each other. This one is like closer to this value, while having just like a global change was 5%. So it could be like the above one, the right one. But now looking into the time, we can see like that this technique, like it took like 18 seconds instead of 20 seconds here, and we used already like much like a lower amount of RAM, which is good. And as you can see, the number of elements and nodes used to get this value, which is like actually perfect compared to this one, which is we got like from our mesh study, Convergence. Actually it's perfect. So I'm gonna actually to get this out, and actually the winner in our study, it's the local mesh refinement using the phase sizing. It could not like be like as like always that this is the best for every situation, for every scenario, but in our model it was the best. As you can see, we got like a very good like a value or a stress value, which is like too near to the exact one or the best one. We solved like so fast, and we got actually, we use like almost, if you compare to the first like technique, which is using the initial coarse mesh, so we have like about like 50 megapascal like as a difference, which is huge. And we use like the same, so the solution time was the same, almost the same like amount of memory used, also like a slightly bit more like number of elements are not, but still like too low actually. So the winner in our study now is the local mesh refinement phase sizing. So this is very interesting. So I'm gonna now like if you found this like if you found that this could be like in other cases also, like as an alternative. I don't have like something against that. You can use it for sure. You can use every something else for sure, but you will like this will cost you like more computational like time and so on, and more RAMs, for example, without like any necessity. So which refinement method do you usually use? Let me know in the comments. And actually, mesh refinement isn't about creating the finest possible mesh. It's about creating the smartest mesh. So in our model, and as you already saw, actually you have first to understand your model, where to expect the stresses, or even when your model is complex and you don't know where the highest like location where we get the highest stresses, you can do a first calculation, and based on that you can like adjust or enhance the second simulations. So understanding where stresses occur, recognizing like stresses gradients, and choosing the appropriate refinement techniques are skills that separate experienced simulation engineers from beginners. I hope this tutorial like helped you understand not only how to refine a mesh in ANSYS Mechanical, but also why each method matters. If you found this video useful, please give it a thumb up. It's really helped the channel. And if you like to see more practical engineering simulations, advanced ANSYS tutorials, optimization techniques, real-world like FEA case studies, make sure to subscribe and turn on notifications so you don't miss the next video. Thank you so much for watching, and I will see you on the next one.